Okay, so welcome to the second talk of the second day of the Fibonacci Springboard stuff. And so hopefully all the technology will be working. What I want to do now is talk a little bit about applications of art and math and trying to do things efficiently, seeing some good pictures and whatnot. Because I had 25 seconds notice about lecturing on this, I am going to steal slides from myself from years ago. This is a talk that I've given many places that I like, and we'll just choose which parts to go through. But again, if you want to see more details, happy to do so. Some of it depends on doing some calculus, but a lot of it can be done at a variety of levels. Okay, so hopefully you've heard about, yes, so I'm actually fortunate enough to know him from when I was an undergrad at Yale. There are certain systems that are extremely chaotic, but very small changes in initial conditions very rapidly lead to wildly different behavior. One of my former students works on climate studies. I'm not going to go into the politics of climate change. I will just say that a lot of the models are extremely sensitive to the values of the parameters. And this makes both prediction and policy questions extremely difficult, because if your models are very sensitive and these values are not exactly what you think, whereas for other things, it doesn't matter too much. I can always make a little bit of adjustments later. The gross behavior won't change. If you have a pendulum that swings, how many equilibrium positions does a pendulum have? So a lot of people say one. One is incorrect. If it's hanging down, it is in equilibrium. And if you move it ever so slightly, it has very small changes in behavior. So it's a pretty stable equilibrium. A small change doesn't really change the behavior that much. There is another equilibrium position for the pendulum.
Are there three?
All the way at the top, straight up. That's an equilibrium. However, if you now hit it ever so slightly, you're going to get wild swings and wild changes in motion. So that's the danger in analyzing something like that. All right, so I'm not going to go through a lot of the stuff. So the first part of the talk is about defining dimensions. This is not a bad thing to do in a class like this. We use so many terms without really knowing what they mean. It's the, I'll know it when I see it. So does anybody want to take a shot at defining a word such as dimension? Like, what is the dimension of an object? And if you can't define it, give me examples. You know, what are the possible values for dimension if you can't?
Length times width times height.
Okay. Okay. So one thing is, you know, we have a bunch of different quantities, and then we can multiply them together. So what possible values could dimensions be?
It's hard to answer that. It's going to be anything.
Well, I mean, do you want to consider a 2 by 3 rectangle different than a 5 by 7 in terms of dimension? There's two different ways to interpret dimension. I don't mean dimension in terms of area. I mean dimension in terms of, not direct, but maybe like, well, form might be better. So instead of looking at a rectangle, what could I look at? Triangle. But would a triangle and a rectangle in some sense have the same dimension? They're both two-dimensional, right? And instead of a two-dimensional object, I could look at a three-dimensional. You know, so I could have, you know, a box versus a plane versus a line. So what kind of values could dimension take on? So I agree that a rectangle, you could give its dimensions as length and width, but we would view a rectangle as a two-dimensional object. So what kind of dimensions could we have? We have two-dimensional objects, we have three-dimensional objects.
Are you mean like area and volume?
Right, so area would be two-dimensional objects would have areas, three-dimensional objects would have volumes. So what are the possible values for dimensions? You know, we said a rectangle and a triangle. Well, we said rectangles and triangles are both two-dimensional objects. So the dimension would be 2. A box, we would say, would be a three-dimensional object. So what kind of values can I get for dimension?
Integers.
Integers. What kind of integers?
Oh, no, intermediate.
Positive, right? I'm not gonna have a negative 3-dimensional object,
Okay.
right? I'm not gonna have a root 2-dimensional object, right? So here's an interesting way of defining dimension. And again, this is mathematicians, being very rigorous and whatnot. So Blackboard R just means the real numbers, R2 means pairs of real numbers, and so on and so on. We say that if we dilate a set by R, that means we multiply each point by R. So if I have a sphere of radius 1, if I dilate it by a factor of 2, I now have a sphere of radius 2. If I have a 2x3 rectangle and I dilate it by 2, it's now a 4x6 rectangle. So I'm just multiplying, I'm just stretching everything by the same factor. And so if I give you a set, S, which is something that lives in n-dimensional space, if I dilate it by a factor of R, I'm taking every point and I'm multiplying every point by R. So if I have the interval from 0 to 1, I would now have the interval from 0 to R. Okay? And so if dilating S by a factor of R yields C copies of S, then the dimension D of S satisfies R to the D equals C. Right? This should look like gobbledygook at this point. Right? You can at least understand what the words are. Okay, R is the dilation factor, C is the number of copies of the set I have, D is the dimension. Does this formula make sense to define dimension? How can we see if this is reasonable? What could we do?
Square.
Try a square, right? So what's the easiest examples? Let's try a square. Well, square is not the easiest. Easiest would be a line segment. Then we'll work our way up to a square. So if I take a line segment of length 1, if I triple it, I dilate by a factor of 3, I now have a line segment of length 3 because I'm stretching it by a factor of 3. So 0 goes to 0, 1 goes to 3. So does everybody see that if I dilate by a factor of 3, I now have 3 line segments, all the same as the original? And so if I look at my formula, R to the D equals C, 3 to the what power equals 3? 3 to the first power. A line segment would have dimension 1. That's good. Now we'll go to David's horrendously difficult example of a square, right? So if I take a 1 by 1 square and I dilate by a factor of 3, we now have a 3 by 3. We have 9 copies of our original 1 by 1 square. So we're trying to solve 3 to the dimension equals 9. Okay, 3 squared equals 9. You could do this for the box. I could do the drawing for that. Once we get beyond the box to the 4-dimensional, I'm going to have trouble, but the pattern is hopefully clear. So dimension, this is at least working like what we would expect. And locally, if I give you anything 2-dimensional, there's a little square that should be part of it. This seems like a decent definition. So here is a strange example of something that has a non-integer dimension. So this is called the Cantor set. And you start off with the interval 0, 1, and then you throw away the middle third. And when you throw away the middle third, you then have 2 segments. You have the segment from 0 to 1/3, and then you have the segment from 2/3 to 1. And now, like we did in the first class, we do lather, rinse, repeat. We have 2 segments. We throw away the middle third from each one of them. And so now we have 0 to 1/9. We lose 1/9 to 2/9, but we have 2/9 to 3/9. And we keep doing this, and we keep doing this. So every segment for the next level, we throw away the middle third. And we can ask what happens in the limit. So what do you think is going to be true? What's the length of the original segment? 1. What's the length after 1 iteration? Not half.
2/3.
2/3. What's the length after 2 iterations? 4/9. You lose 1/3 every time, you keep 2/3. So we go length 1, then we have something of length 2/3, and something of length 4/9. If we do another iteration, what would the length be?
There's 8 pieces now.
There'd be 8 pieces now.
Maybe 1/27. So 8/27.
Or 2/3 cubed. Every time we do another level, we keep 2/3 of what we had. We throw away 1/3, we keep 2/3. So at each level, we keep 2/3. What's the length going to be in the limit? 0. 1, 2/3, 2/3 squared, 2/3 cubed, 2/3 to the 4th, 2/3 to the 5th. In the limit, do you agree that the length is going to be 0? Yeah. So this is something whose length would be 0. So the dimension of this cannot be as large as 1. But we could play the game on dimension that I discussed earlier. It turns out that there's infinitely many points here. And as an aside to those who do computer science, what base do you love? Binary. We love base 2. If you think about what's going on, I throw away everything from 1/3 to 2/3 in the first iteration. That's throwing away all numbers whose base 3 expansion starts with a 1. At the next level, when I throw away the middle thirds, I'm throwing away all the numbers whose second digit in their base 3 expansion has a 1. I'm looking at all numbers whose base 3 expansions don't have a 1 in it. There's a 1-to-1 map, and again, it's okay if this goes over your head. There's a 1-to-1 map between numbers that don't have a 1 in their base 3 expansion and base 2 expansions of numbers. Just divide the numerators of each digit by 2 and replace the 3 to the end with 2 to the end. So this set has the same number of points as the entire interval 0, 1, but it's arranged in such a way that it has length 0. So there's a real difference between cardinality and dimension. Again, this is not every moment of every talk needs to be accessible to everybody. I just wanted to throw this out there. The length is going to be 0. We keep throwing away more and more things, but there's infinitely many points. And in fact, there's as many points as the entire interval. This is bad. Let's try to think of what happens. Can anybody think of a good factor to dilate this by? Good integer to multiply everything by. So we're throwing away the middle thirds. What?
3.
3. So if we dilate by a factor of 3, then this segment over here expands out and becomes the whole thing. This whole thing that's missing expands out and becomes a segment of length 1 that's all missing. And then this whole thing on the right expands out and becomes another copy of the whole thing. So if we dilate by a factor of 3, how many copies do we get? 2. And so we would then solve 3 to the d equals 2. So d is the log of 2 base 3, about 0.63. So we would get a non-integer dimension.
What does the word dilate mean?
Dilate is just, we're multiplying every point by this factor. So if I have a rectangle that's 2 by 3 and I dilate by a factor of 5, it would now be a 10 by 15. I'm taking every point and I'm stretching by the same fixed amount. So as a nice aside, does anybody know what triangle this is? Yeah, good. If anybody didn't get this, this would be really embarrassing, right? This is Pascal's triangle. We've been playing even odd games all the time. Have you ever played even odd with Pascal's triangle? Let's remove all the even numbers. Okay. So we're going to put a dot if it's odd, and we're going to leave it blank if it's even. Okay. And so if we had just one row, we would just see a dot. If we have 4 rows, well, it goes 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. The only even number in the first 4 rows is the 2 in row 3. And then we could ask, what happens if we keep going, if we keep going, if we keep going? This is what happens if we do it a little bit more. Anybody notice anything?
The center is dilated. Copies.
They're copies. It looks like what we have on the top is repeated on the bottom left and the bottom right. And so I hadn't been able to find a video on this. So I actually made a video years ago. Initially, I did it so it was oriented going from left to right. I eventually fixed it to go top to bottom. I'll be sending these slides. So if you want to, you'll play these videos. I guess I don't want to. I'll risk it. Okay, so the video is not showing up, correct? Let's try it. I apologize, there is no cheesy music. And so here you should be able to see 3 dots. And what I'm going to do is I'm going to keep adding more and more rows, and I'm only going to keep the odd numbers. Now, I went to Yale. Yale is a much better institution than Harvard. And at Yale, we would have, of course, an infinitely long data screen projection system. But Harvard's endowment is not quite sufficient for something like that. So I only have so much screen to work with. I can't keep adding more and more rows without compressing things. So in the interests of space, I will keep compressing things to always display in the same square. And let's see what happens as we add more and more rows. So hopefully this will run. Okay, good. And you can start to see what's happening as more and more rows are being added. I feel like it's the beginning of Star Wars. You see the Imperial Star Destroyer coming in. And so it's a fun program to try to write this and try to write this efficiently. And again, if you're teaching computer science, you don't need to calculate the binomial coefficients. You only need to determine if they're even and odd. And so it's a really interesting recursion problem to try to write this efficiently. But what you can see now is you can begin to see, oh, this upper left thing is then repeated. The top is repeated, bottom left, bottom right, and then that whole segment is repeated, and those whole segments are repeated. It seems like there is a fractal structure here. And so hopefully going back here. Yes, okay, good. So we can try to figure out what is the dimension of the Fibonacci triangle mod 2. Well, let's play a game very similar to what we did with the Cantor set. And this hopefully will be a little bit easier to visualize than the Cantor set. So we take an equilateral triangle and we divide it into 4 smaller equilateral triangles and we throw away the middle. And then each of the 3 triangles remaining, we divide into 4 equilateral triangles and we throw away the middle. This is very similar to what we did with the Cantor set. But I can now draw the picture, I think, very nicely. Can somebody give me an upper bound for the dimension on what's left? I love asking questions like this. Don't solve the problem. Give me an upper bound. The dimension is no more than what? Could the dimension be 2025?
Why not?
So that's what I'm asking. Can you give me a reason why not? Where does this shape live?
Within the constraints of the one.
Okay, and where does that one live?
It's 2-dimensional.
It's 2-dimensional. It lives on the plane. So what should be an upper bound for the dimension of what's left?
Less than or equal to 2.
Should be less than or equal to 2. It shouldn't be something greater than 2 because it lives in the plane. Can you give me a lower bound on the dimension? It should be at least what?
Greater than 1.
Greater than 1. Why is it greater than 1?
Can't draw it in 1 dimension. We can't draw out just the line.
Maybe we could. But can you see a line that's always kept?
Just the bottom line.
Bottom line, the 2 side lines. I'm never removing anything on the outside. So it should be at least 1-dimensional. It should be at most 2-dimensional. So again, I really try to emphasize for students, have some feel for what the answer should be. This should be somewhere between 1 and 2. Now I need to figure out what should I rescale by? What should I dilate by so that I get a good number of copies? Anybody think of a good factor?
Like a large factor?
Yeah, to rescale things. I'm sorry? 4, but there's something better than 4.
10?
Why 10? See, as soon as you say 10, I'm thinking fingers. I'm thinking humanity. Right?
Yeah.
And so we're trying to look at symmetries here. So we're dividing things in 4s. But how are we dividing things in 4? We're making 4 pieces. But how are we determining where to put the cut?
Oh, like
in the middle. So instead of rescaling by 4, what should we rescale by? By 2. And then everything from 0 to 1 would expand from 0 to 1/2, I'm sorry, would expand to 0 to 1. So if I double everything, the triangle in the bottom left expands out to fill the whole thing. The triangle in the bottom right expands out and makes another copy. The triangle in the upper part, the top, expands out and makes another copy. And then the empty region expands out and makes a completely big empty copy. So if I double, how many copies do I get? 3. And so now, trying to solve r to the d equals c, if r equals 2, I'm dilating by a factor of 2, I'm getting 3 copies. I need 2 to the d equals 3, so d is the log of 3 base 2, which is greater than 1 and less than 2. So the answer is reasonable. So we could say that the dimension of this would be a fractal number. And it turns out you can take any real number and you can construct something with that dimension. It's a fun problem. And I gave that to one of my students years ago. Okay, so there's lots of ways you could generalize this. You could look at Pascal's triangle mod 3. You could do it mod 4. You could ask about the different patterns that emerge. And so I'm not going to go too much, but another fun one is the coastline paradox. What is the dimension of the coastline? What is the length of the British coast? And so here's a great example. Imagine you want to measure the coastline and you're going to use a 200-kilometer yardstick. Or I probably shouldn't say yardstick if it's 2,000 kilometers. We'll say a 2,000-kilometer measuring rod. Are you going to be able to measure nooks and crannies well? No. And then what we can do is when we do that, we do the best we can, and we get the length is about 2,400 kilometers. We could then have it and use a 100-kilometer rod, and then we would get the length is approximately 2,800. Then we could do a 50-kilometer, and we would get 3,400. So the question is, will this go off to infinity as you make it smaller and smaller and smaller? Will it stabilize? Do you think some countries might have a higher dimension for their coastline than others? Anybody have any guesses as to which countries might have a very high dimension for their coastline? So some geography, which countries might have a very jagged coastline?
We've got an answer in the chat.
Oh, I've got an answer in the chat. Thank you. So in the chat, you can actually just say things like Norway is excellent. Finland might dispute that and they might want to be listed first, but Norway, Finland, Sweden, countries like that would be really good. And so you could actually look at what is the coastline dimension in different places. I'm not going to go through this. There's lots of different examples. This is the Koch snowflake, where you take every segment, throw away the middle, and put a triangle and keep iterating. And you will get an object that has dimension greater than 1, less than 2. All right. This is where things are now going to get a little intense. But again, we're going to get it done before lunch. Okay? There's a lot of good math going on here. And in fact, the math behind this, I was torn between being a mathematician and being a physicist. I majored in both, but it was a problem related to this that just pushed me into math. All right. Much of math is about solving equations. And if you're lucky, you even know what the equations are and what the values are in the equations you're trying to solve. You know the values of the coefficients. Not always the case. So if I give you polynomials, we have ways to solve them, at least if the degree isn't too bad. Ax plus b equals 0, move b over to the other side, divide by a. We'll assume the leading coefficient is not 0, x is negative b over a. If I give you a quadratic, there are ways to get to the solution of the quadratic. There are formulas for the cubic and the quartic. There is no closed form expression for degree 5 and higher in terms of the coefficients. This is a major result. For definiteness, here is the formula for the cubic. Nobody memorizes this except for people who have issues. What could you do to make this formula a little bit easier to remember? What kind of simplifications can you assume? Without loss of generality, I might as well assume this coefficient is
You divide it by a third.
y a third.
Well, I'm looking at, I can barely see it, but I'm looking at 2 1/3,
Mhm,
and then b over 3a,
mhm.
and everything. Then on the bottom there's everything. Well, it's cubed, so it's a cube.
Well, there's cube roots. So if I look at the coefficients a, b, c, and d, without loss of generality, what can I assume about one of the values? A, B, C, and D don't have to be integers. They're just numbers. I claim one of the numbers I can set without any trouble.
Assume A is 1.
You might as well assume A is 1. Because it's a cubic, the coefficient of x cubed is not 0. Just divide through by that and make things a little bit easier. So you can actually replace all the a's with 1s. Without loss of generality, I divide through by a. You can then translate and you can actually set b to be 0. So with a little bit of work, we can always assume a is 1 and b is 0. So in the old days, mathematics was a sport. And you could actually challenge people for their professorship. And the way it worked is you would give them challenge problems and they would give you challenge problems. And if you could do theirs and they couldn't do yours, you win. And so the person who discovered the formula for the cubic kept this in reserve. And so again, since you said you're computer science, one of the big things in computer science is sometimes it's hard to solve this problem, but it's very easy to verify a solution. So factoring, we don't know a fast way to do it. There may be, we don't know. Quantum computers have fast ways to do factoring. But it's very easy to check and see if you factored a number correctly. How would you check to see if somebody factored a number correctly? Multiply them all together. Divine inspiration told me this is the factorization. Okay, let me see. If I multiply them and I get the answer, and that's the answer. So what Tartaglia did is he just kept the formula secret. And he doesn't have to divulge the formula to give the answers. You can say, here are the roots. Now, one thing that is interesting is, could you sniff out his formula by getting certain answers from him? So you might have to be a little bit careful. As a nice exercise, you could play the game with, imagine you give him any sequence of cubics you want and he has to tell you the factors. Can you use that to figure this out? Can you do enough special cases? All right. But everybody sees I can fit the 3 different roots on the slide. Here's the quartic. And what you'll notice for the quartic is I can only get one of the roots and I have decreased the font size. Without loss of generality, what can we assume about A? Exactly, yeah. A is 1. And I can also translate and make B equals 0. Even with that, it's still going to be painful. Okay? This is the quartic. We can't find a closed form expression for degree 5 and higher. So one of the big things in math is if we can't solve it exactly, can we approximate the solution? And so any Star Trek fans here? Oh, this is sad. Do people know about the transporter in Star Trek?
Yeah.
Okay, what does the transporter do?
Takes you to a different time. Right?
Not a different time, different place. It moves you from one place to another. It's not quite instantaneous, but effectively. Does anybody know why they created the transporter in Star Trek? When in doubt, follow the money. They didn't have money when they were making the show initially to have a shuttlecraft. That would be an expensive set. They didn't get the shuttlecraft till later. What if we just push this button and then all of a sudden they're now on the planet's surface? Oh yeah, we could put something like sugary stuff over. Yeah, that works. Yeah, let's do that. So a continuous function doesn't have a break. You can't get from one point to another without passing through the intermediate points. So if I start off and I'm negative at 0, and then I'm positive near 1, what can you tell me happens in between? You have to cross. So this is, in fancy speak, this is the intermediate value theorem from calculus. If I start off at one value and I end at another, I have to hit all values in between if I move continuously. If I move discontinuously, I can just jump from here to positive values. So a continuous function would have to cross. So here is a way to find roots, to find solutions to equations. If it's positive at one point and negative at the other, then it must cross. So if I want to find where does f of x equals 5, look at f of x minus 5 and try to see where's that 0. So this is the divide and conquer. So what we'll do is we'll look halfway in between. This is writing it in math speak. It says, look, assume it's negative at a, positive at b, then there must be a root between a and b. Look at what's going on in the middle. Either that's a root, or if not, it's either positive or negative. If it's negative, then there's a root somewhere between there and the end. If it's positive, it's somewhere between there and the beginning. And then shampoo mathematics again. I'm really big on this. Not for myself, of course, no. Sorry, that's being recorded. I, of course, lather, rinse, repeat. So imagine f of 0 is -1, f of 1 is 3. We know it has to cross somewhere in between. Let's look in the middle. Imagine f at the middle is 2. So now we know it was positive at 2, it was negative, it was positive at a half, it was negative at 0. It must cross in between. So we keep going. So now we look at a quarter. And when we look at what's going on at a quarter, that was negative, so there has to be a root somewhere between a quarter and 1/2. So we'll try 3/8. So we keep going, we keep going, we keep going. So one question is, how quickly will this work? And this will lead to good mathematics. This will lead to good art, I promise. Okay, so let's do 10 iterations. And it is a shame that I just lost my computer scientist. How many megabytes are in a gigabyte? I can't remember if we did this last time. Okay, so how many megabytes are in a gigabyte? So who remembers their prefixes? To go from mega to giga. 9.
Okay, so that's.
So 1,000. It's actually 1,024 because computer scientists love to work base 2. And 2 to the 10 is almost 1,000. So we will just appropriate the prefixes. And we'll call it megabyte, gigabyte, but it's really 1,024 megabytes in a gigabyte. So here is doing 10 iterations of this divide and conquer. Every time we do divide and conquer, we take this interval of uncertainty where the root lives, and we cut it in half. And we cut it in half, and then we cut it in half. So if we do this 10 times, we now have an interval roughly of size 1/1,000. It's actually 1/1,024, but roughly 1/1,000. So every 10 iterations gives you 3 additional decimal digits. So if I want to get the square root of 3, which is approximately 1.7320508075688. I have to teach till what time today? So you can just fill it up by rounding off these digits. If I do this 10 times, I'm getting that it's somewhere between 1.732 and maybe 1.730. So I'm getting pretty close. I get 3 decimal digits every time I do divide and conquer, every time I do it 10 times. So 10 iterations of divide and conquer. Each time you have your uncertainty. 10 iterations is 1/2 to the 10th, which is roughly 1/1,000. So if I wanted 9 digits of accuracy, how many times would I have to do this?
9.
Yes, if I want 9 digits of accuracy. So 10 iterations gave me 3 digits, gave me a factor of 1 in 1,000. I'm sorry?
1,000.
Not 1,000,
10
not 10.
times 3, 30.
10 times 3 is
30.
30. Every 10 iterations gives me another 3 digits. So I would have to do this 30 times to get 9 digits accuracy.
That's a lot of work.
That's a lot of work. All right, so now, hopefully everybody has seen equations of lines. And so a lot of this is, I've got slides for this. I have a tremendous amount of desire to talk to people. So I don't want to go into all the details. It's there in the slides. I have other videos of this. Happy to chat with any of you who want to try to work this in. If you're teaching a calculus class, they should know what a line is. They should know how to write the equation of a line. But there's just some reviews here. One of the main points of calculus is that locally any differentiable function looks like a straight line. And if you don't know what calculus is, if you haven't done that, not a big deal. The idea is that we can often approximate a function by a straight line. Locally, that works well. So imagine you are driving from Boston to Miami. and I want to know how fast you're going at a particular moment in time. I can look and see how far you've traveled, and I can look at how long you've been on the road, and I can divide them. Do you think that will be a good estimate of your speed at a given? No, why not?
Traffic.
Traffic, right? Are you near a city? Are you on the highways between? What if I look at how much distance you've covered in a minute? Should that be a reasonable approximation for your average, for your instantaneous speed?
No.
What about in 10 seconds? What about in a second?
It's getting better every time.
It's getting better every time. What about 1/10 of a second? Does your car change speed that much in 1/10 of a second? No. What about 1/100th of a second? Unless you all of a sudden just hit a car in front of you, your speed is not going to change that much in 1/100th of a second. The smaller the window, the more accurate the estimate of your instantaneous speed. But again, I don't expect my instantaneous speed and that approximation to work over large distances, over large times. It's a local phenomenon. What we do is if I give you some function here, is the function f of x is 2x cubed minus 3x plus 1. And what I can do is I can calculate at the point 4 what the value of my function is, and I can find what is the best fit line at that point. So what I'm really doing is doing some calculus. In calculus, if f of x represents distance, f prime of x represents speed. Out of curiosity, how many people have not done calculus? Okay, so if you want, it takes about an hour to learn calculus without going into all the theories and proofs, but the main thing is we have some rule which, given a function f, gives you a new function which will denote f prime to say that it's related to f. And the rule is if I have a polynomial, what you do is you leave the constant unchanged, and when you have x to a power, you bring the power down and then decrease the power by 1. So the 2x cubed becomes 2 times 3x squared. The negative 3x becomes negative 3, 1 times x to the 0. And the one over here, it just goes away because I have an x to the 0, which is 1, and the 0 just comes down. So it turns out that this is a rule that will give you the instantaneous speed at a moment. Right now, all that matters is we just have some way of finding what's the best line to the curve at this point. What's the line that comes closest to approximating this complicated function? Okay, and what Newton's great idea is why don't we just replace the function with the straight line and see where it hits? And let's call that the root. Do you think that's going to be the root? Unlikely, but hopefully it's close. And if it's close, what could we then do? Shampoo, lather, rinse, repeat, right? I don't have that many tricks. And so again, I could take another function, I can keep playing this game. And so what Newton's method is this is where you get very carefully, is you take a continuous and differentiable function. You find the best fit tangent line approximation, you see where that hits. And that's your next guess for the root. Then you evaluate the function at that point, find the best fit tangent line, and see where that hits. And then you keep going, and you keep going, and you keep going. You get this sequence of approximations. What should we compare how well this does to? The divide and conquer. Which do you think does better, divide and conquer or Newton's method? Could depend on the function. Well, this is Newton, right? The other thing is, for divide and conquer, what did we assume about the function?
It's linear.
Not linear.
A was 1.
So we were doing the no transporters. What were we assuming about the function? Linear functions are this, but it's continuous, right? So for the divide and conquer, we were assuming the function was continuous. So if it was negative here and positive there, it had to hit. Here we're assuming the function is continuous and differentiable. We're assuming more. Not every function is differentiable. So the hope is that by assuming more about the function, we can do more. And so here is the first iteration of of Newton's method. We start off with our initial guess x naught, we draw the line, we see where it hits, and then law difference repeat, we draw the next line. And you can actually go through and you can come up with an explicit formula. So if x squared minus 3 is my function, when does this equal 0? So when does x squared minus 3 equal 0?
Never. Oh, at 0.
Well, when you put it, when you put an x, when you put an x equals 0,
Yeah,
you would get
never.
-3. Is there any value of x? Doesn't have to be an integer. Any value of x such that x squared minus 3 is 0?
Because x squared always has to be positive.
This.
Wait. But you're trying to get x squared minus 3 to be 0. So if x squared minus 3 is 0, that's the same as x squared equals 3. Square root of 3. And what else would work?
Negative square root.
Negative square root of 3. So there's two things that work. So it turns out you get the following explicit formula for your next guess. And this is what made me decide to be a mathematician. 1/2 x to the n plus 3 over x to the n. What would be an interesting choice to take for xn? We're trying to find the root of x squared minus 3. I claim there's a really good choice to take for xn. Square root of 3, excellent. Then we get root 3 plus 3 over root 3. What's 3 over root 3? 3 divided by the square root of 3 is root 3. Root 3 plus root 3 is twice root 3. Divided by 2 is root 3. If you're at the root, you stay at the root. So we were talking a little bit in the unrecorded intermission about fixed points. Root 3 is a fixed point here. If you put that in, you stay there. So if you happen to find the root, you don't leave the root. What if we take something like 100? That's way more than root 3. 100 plus 3 over 100 is approximately 100, right? Thank you. Don't make me do terrible, painful arithmetic. So if I take xn equals 100, I would get 100 plus 3 over 100 divided by 2. That's about 50. And if I take 50 plus 3 over 50, that's still about 50 divided by 25. 25 plus 2, about 12.5. You can see it's very quickly falling towards the square root of 3. It's moving very fast. Maybe this has good convergence properties. And so this is just the math proving why it works. I'm going to skip that. And so here, I'm trying to find approximations to root 3. One of the things that's nice about this is for this problem, you're always going to get rational numbers. If you're working with a computer, we like working with rationals because that's just working with integers. Does everyone agree that 2 is not a particularly great guess for the square root of 3?
Yeah.
Yes.
Okay, I'm not rigging things, okay? Well, if I use my formula, my guess is 2, so my next guess is 1/2 2 plus 3/2. You know, this is the advantage of preparing lectures ahead of time. So it's 7/4, so 1.75. How is that for your approximation for square root of 3? It's close. What should we do? Shampoo mathematics, right? Do it again. So 1/2 7/4 plus 3 over 7/4, which I know you've all done in your head as 97/56, which is 1.73214. The correct answer is 1.73205. So we're off by 0.00008 roughly, 9, something like that. Not bad. What should we do? Do it again. And so we get 18,817 over 10,864, which, of course, in your head you can do is 1.732050810. 1.732050876 is the right answer. We're off by 0.00000000024. After 3 iterations, starting with 2, and we even have it as a rational number. This is what made me, go into mathematics. To see something that works this well. It turns out for problems like this, every iteration you double the number of digits. So divide and conquer, we work hard, and we get 3 more digits every time we do 10 iterations. Here we double the number of digits. And so just to be truly impressive, the 5th approximation is x5. You can see I put in black just how far you have to go before you finally find a digit.
Oh my gosh.
Yeah. I don't know why the light is not showing up, so I'll just use my finger. Apologies for those in Zoom land. You got to go really far to see a digit that's off. And this is just 5 iterations of Newton's method. And we even have an explicit rational. Now, this is great math, but the challenge was to do math and art, right? And we haven't done too much art yet. So let's play a game. I love games. So we're going to take, instead of x squared minus 3, I'll do x squared minus 1. Everybody should hopefully be able to see that the roots are 1 and negative 1. And I'm going to color everything that iterates to the root of negative 1 red, everything that iterates to the root of positive 1 blue. And you have to tell me what color everything is colored as we play this game and we iterate. So if I start off with 100, which do you think 100 is going to converge? And if so, what do you think it's going to converge to, 1 or negative 1? 1. What if I start with negative 100? What do you think it will converge to? Negative. And in fact, you can look that if you start positive, you stay positive. If you start negative, you stay negative. So nothing positive can ever converge to negative. Nothing negative can ever converge to positive. But it may not converge. It may not go to 1. Does anybody want to tell me what numbers they think will converge to 1?
Strictly positive.
Strictly positive. Strictly
large numbers, larger numbers.
Larger numbers. But what if I give you a number like 1/10? If I give you 1/10, I get 1/10 plus 1 over 1/10. Oh, well, 1 over 1/10 is 10. So this would be a little bit more than 5. So if you start with a small number, after one iteration, you become large. So I can see as a reasonable conjecture, positive numbers go to 1, negative numbers go to negative 1, and what about 0?
It's 0. No. Yeah.
So what happens if I try to put, it's undefined. So 0 is the battleground. Nothing can be done at 0. Okay? All right. Let's make the game more interesting. All right. So let's look, instead of x squared minus 1, let's look at x cubed minus 1. So for this, we need complex numbers. So I either is or am the square root of negative 1. I'm sorry?
I don't know, I'm just laughing.
Do you know what they say about complex numbers? It's an old joke. It's only fun till someone loses an eye. So I can write any complex number as a real part plus an imaginary part. And I can write it as x plus iy, where x and y are real numbers, I is the square root of negative 1. And we can try to find what are the roots of x cubed minus 1. So who here teaches algebra? Okay, so you might teach them like the rational root test.
We do. We just use patterns.
Okay.
Where they're going to do x minus 1, and then we use what we call sofas,
Okay,
where you square your first opposite sign, first times last,
Okay.
always positive, square the last.
okay,
So you get x minus 1 times x squared plus x plus 1.
yes,
And then you'd set each of those equal to 0. and
Correct.
solve.
and so this would be linear, this would be quadratic, so we reduce the quadratic formula, so excellent. So this is something that you can easily give your kids. You could also do long division,
Yes.
and there's lots of ways to do this. And we get that there's 3 roots: 1, negative 1/2 plus I root 3 over 2, and negative 1/2 minus I root 3 over 2. And so now we can play the game. We have 3 roots, and we can use Newton's method, and we get the same formula, and we can ask, which do we go to? And we will color them red, green, and blue. And so now you have to tell me, which points do you think will go to the red, which will go to the blue, which will go to the green? And if you can't answer that, can you tell me maybe something about the shape, any kinds of symmetries you might expect? Do you think more go to one color than another? And if so, which color? Or do you think all the roots are equal?
If it's a cube root, then it has to go into both, right? I mean, 'cause it would.
Well, but I'm playing the game, so remember, a little bit earlier, we were playing the game of you give me an initial seed, so the number you choose is the x0, and I keep playing this game, and eventually it converges to either 1 or negative 1. If it's positive, it will always converge to 1. If it's negative, it will always converge to negative 1. It doesn't have to converge, and 0 is one that does not converge. And so here, I want to play the game now, but with these 3 points. And so I'm going to apply a generalization of this. I'm not showing you what formula I'm using. And I want to know, will it converge to red? Will it converge to green? Will it converge to blue? Do you think any root is going to be more than the others?
Feels like it should have like threefold rotations.
So it feels like it should have threefold rotation symmetry, that if I just rotate everything, it should really be the same. Can anybody give me any thoughts as to how you determine which one you go to? Another way is, can you give me a nice simple rule to say which goes to 1, which goes to -1? You go to the root that is closest, right? Look at small cases and build some intuition. So if you go to the root that's closest, what do you think would go here? How do you think you determine which root you go to? You go to the root that is
Closest.
closest. So how would I figure out which root you're closest to?
Just find all the distances.
So how would I divide up the plane into which are closest to red, closest to green, closest to blue?
Positive and negative. I mean,
Real
versus.
I'm sorry? So now here's the art. Where do you draw the lines to divide this into 3 regions? Where one region is the region that's closest to red, one is closest to green, one is closest to blue. Any thoughts? Well, let's take 2 points. How would I determine if you're closer to red or green? Which positive or negative?
Whether you're positive 3, 2/3, the one high.
So I'm looking at the red, which is, and the green. So how do I determine if I'm closer to the red or the green?
So one of them you add 2/3 I, and the other you subtract 2. I don't
Yeah.
remember what the roots were.
Yeah, the roots were, oops,
Sorry, the red and the green.
was I √3/2 and minus I √3/2 for the
Yeah.
imaginary parts. So what's a simple rule to see if you're closer to red or green?
Imaginary part positive.
Is the imaginary part positive? If the
Yeah.
imaginary part is positive, you go to the red. So I would say, there should be at least some line coming through here on the x-axis, and if you're above the line, you would go to red over green. But that doesn't answer how I determine if I'm going to red or blue or green or blue. So how would you determine if you're going to red or blue?
Rotate the line, like 60
Rotate the line. And so if I draw the line, if I take the line from red to blue and find the point in the middle and draw a perpendicular, this is going to give me 3 segments. And so everything in the segment to the right is going to go to blue, everything in the segment to the left is going to go to red, and everything in the bottom is going to go to green. And so we should have a nice picture with 3 distinct regions. Does that count as pretty geometry for you? Well, you don't have to take it. We do still have 10 minutes left because lunch is at noon, right? That's what you get. This is the coloring. Very different than what you would expect. And so what this means is each point in the complex plane is colored by which root they go to. And you have the ridiculous situation that you can be very far on the left. And if I move ever so slightly, I change, do I go to the red root, the blue root, or the green root? This is extremely sensitive to initial conditions. And so like everything else in life, you can eventually find a good YouTube video. Fortunately, I did not have to create this video myself. And so I don't know if this one has the cheesy music. And so this is, oh, shoot, wait. I forget. When I switch over here, sadly, I have to then go back and change the share. Okay, is it showing? Okay, good, now it's showing, okay. And you can see what's happening as you zoom in. And what this is showing is extremely small changes in the initial condition lead to wildly different behavior. And there's a lot of symmetry. We've been seeing symmetry up the wazoo for the last few days. To prove a lot of this stuff becomes very hard. You should notice some interesting now, almost hexagonal symmetry coming in as we zoom in like this. It's a challenge sometimes to even compute stuff like this. And if people are interested, one of the things we can talk about in the afternoon is how do you compute stuff like this quickly? We have a lot of brute force algorithms that will work, but they might be slow. Divide and conquer, every 10 iterations gave us 3 digits. Newton's method, you doubled the digits every time you do it. And it's one of the easiest examples to very quickly show this incredible sensitivity to initial conditions. If you remember the pandemic response, one of the big things people were talking about is how many people does each infected person infect? Does anybody know what you call that number? The R, right? And so if R is less than 1, this is good. Each person on average is infecting fewer people, so the virus will die out. But if the number is greater than 1, it's bad because you're going to be exponentially growing. So this is where very small changes can make a huge difference in what happens. So there's a lot of great stuff like this when you're trying to talk with the students about how important is it to know these answers. And when we're trying to understand the pandemic response, a little bit greater than 1 versus a little bit below 1, completely different how you deal with something like that. This is a great way to hammer home the importance of knowing certain things. For other things, we don't need to know the numbers that well. It's not that big of a deal. If instead of trying to solve x squared minus 3 equals 0, I do x squared minus 3.01 equals 0, it's not going to really change things by that much. Okay, so this is a good place to stop and then have a lunch break, and then we will resume at 1 o'clock. Okay. And now, yes.